In part 1, we covered the three foundational single-agent patterns: React for transparent reasoning, Code Act for powerful code execution, and the tool use loop for efficient simplicity. If you missed it, links in the description. But here's the reality. A single agent has limits. It has one system prompt, one set of tools, one context window. Ask it to do a complex migration assessment that requires schema analysis, cost modeling, dependency mapping, and report generation. It's going to struggle. The context window fills up, the instructions conflict, quality drops. The solution? Multiple specialized agents working together. Welcome to multi-agent architectures. Multi-agent architectures distribute work across multiple specialized agents, each with their own system prompt, tools, and area of expertise. Think of it like a team of specialists versus a single generalist. The specialist team almost always wins on complex tasks. There are three core benefits. First, specialization. Each agent can have a focused system prompt and relevant tools, so it performs better in its domain. Second, scalability. You can add new agents without bloating any single agent's context. Third, model efficiency. Your orchestrator can use a powerful model like Claude Opus for planning, while workers use cheaper models like Haiku or Sonnet for execution. The most common multi-agent pattern is Orchestrator-Worker. A central manager agent, the orchestrator, receives a complex task, decomposes it into subtasks, and delegates each one to a specialized worker agent. The workers execute independently, return their results, and the orchestrator synthesizes everything into a final output. Let's make this concrete with an enterprise example. You need to assess a Databricks workspace for migration to EMR on EKS. The orchestrator receives this request and breaks it down. Worker 1, analyze all schemas and table dependencies. Worker 2, build a cost comparison model between Databricks and EMR. Worker 3, map all notebook dependencies and external connections. Worker 4, generate the executive assessment report. Each worker has its own optimized system prompt and relevant tools. The schema agent has database access. The cost agent has pricing APIs. The report agent has document templates. They don't interfere with each other, and the orchestrator handles coordination, error recovery, and final synthesis. The key design decisions. How does the orchestrator decompose tasks? Structured JSON plans work well. How do workers report back? Standardized result objects. What happens when a worker fails? The orchestrator needs retry logic and the ability to reassign work. When the problem space is too large for a single orchestrator to manage, you go hierarchical. A director agent delegates to team leads who further delegate to leaf-level worker agents. Think of it like a corporate org chart, but for AI. Consider a full-stack cloud migration. The director coordinates 3 teams. The data team lead manages agents for database migration, ETL pipeline conversion, and data validation. The infrastructure team lead manages agents for compute provisioning, networking, and storage. The security team lead manages agents for IAM policies, encryption, and compliance checks. The trade-off is clear: more latency. Every message has to traverse the hierarchy. Higher token cost, every agent consumes tokens. But significantly better quality on complex multi-domain tasks because each agent operates within a focused scope. Use this pattern when the task truly spans multiple domains and no single orchestrator can hold all the context. In the peer-to-peer pattern, there's no central controller. Agents pass messages to each other as equals. This might sound chaotic, but it's remarkably effective for quality assurance and decision-making. There are 3 main variants. First, adversarial debate. 2 agents argue opposing sides of a question, and a separate judge agent evaluates the arguments and makes a decision. Second, collaborative refinement. One agent produces output, another improves it, and they iterate back and forth until quality converges. Third, consensus. Multiple agents independently analyze the same problem and vote on the best approach. Here's a practical use case. Agent 1 generates a PySpark migration of a Hive script. Agent 2 reviews it for semantic equivalence. Does the output match the original? Agent 2 also checks for performance anti-patterns. They iterate until both agree the migration is correct. This catches subtle bugs that a single-pass approach would miss entirely. The downside? It's expensive. You're running multiple LLM calls for the same task, but for high-stakes outputs where correctness matters more than cost, debate architectures are worth every token. The swarm pattern, popularized by OpenAI's Swarm framework, takes a different approach. Agents operate semi-independently with lightweight coordination through explicit handoffs. Each agent has its own scope, system prompt, and tools. When it encounters something outside its expertise, it hands off to the right specialist. Think of it like a customer support system. A triage agent receives the initial request. If it's a billing question, it hands off to the billing specialist with full context. If it's technical, it routes to the technical agent. The handoff is explicit. The agent says, "I can't handle this," transferring to the database specialist, and passes along the conversation state. What makes swarms different from Orchestrator-Worker? There's no central planner. Agents self-organize through handoffs. This makes the system more resilient. If one agent goes down, others continue working. It's also easier to add new specialists without modifying a central orchestrator, but you lose the global planning and synthesis that an orchestrator provides. Let's compare all four multi-agent patterns. Orchestrator-Worker is your default choice for most complex tasks. It's the most versatile. Go hierarchical when you genuinely have multiple domains that need independent management. Use peer-to-peer when quality validation matters more than speed. And reach for swarm when you need lightweight routing with independent specialists. That's part 2. You now have 4 multi-agent patterns in your toolkit. Orchestrator-Worker for task decomposition, Hierarchical for multi-domain complexity, peer-to-peer for quality assurance, and Swarm for lightweight routing. But multi-agent systems can be unpredictable. What if you need more structure, more control, more determinism? In part 3, we explore workflow-based architectures, DAG pipelines, state machines, and plan and execute patterns that bring order to the chaos. Follow me so you catch part 3 when it drops. Comment below. Which multi-agent pattern would you use for your current project? Full series playlist in the description.